So we left off, we were talking last time about probability. What is probability? It's the likelihood that a certain event will occur, that something will happen. Probability must be between 0 and 1 if you express it as a decimal. If you express it as a percent, it must be between 0% and 100%. Last time we were talking about computing probabilities involving combinations and permutations, things of that nature. Today, we're going to continue that chat, but we're also going to talk about concepts like independence, conditional probabilities, things like that. So what we can talk about is we can talk about independent events. Independent events, this is going to be a key word here. Two events are independent if the occurrence of one has no effect on the probability of the other one. So if one of them basically does not affect the likelihood that the other one will occur, those two events are said to be independent. We can think of all kinds of events that are independent. There's an old joke, if a butterfly flaps its wings in Europe or in Brazil, will that cause tornadoes here in Texas? Well, no, it really shouldn't. Even if you like that Ashton Kutcher movie, it really shouldn't do that. So what we would say is the probability that a certain butterfly will flap its wings and the probability of a tornado hitting the Dallas-Fort Worth area tomorrow are independent. They don't affect each other's occurrence of happening. You can think of plenty of examples of independent events. Very quickly, actually, which is cool. Let's think of some more examples together. Let's say you draw two cards from a deck, but with replacement. This means that after you draw the first card, you record it. You remember what it is, the King of Hearts or something. You replace it in the deck. You reshuffle the deck and then draw your second card. Those are going to be our independent events. Are they independent? Well, let's say E is the event of drawing a jack on the first card. Let's say F is the event of drawing a jack on the second card. Are these independent? Yes. E and F are independent because we've reset the deck before drawing the second card. That's the long and short of it. We reset the deck, thus these are independent events. They don't affect each other or the probability of each other. The probability I draw a jack on the first card is 4 out of 52. The probability of drawing a jack on the second card is also 4 out of 52 because we've reset the deck and there's nothing more to do. It's basically the same as the deck was in the first place. So the events don't affect each other's probability of occurring. So that's an example of some independent events. Here's another one. Flip a coin and roll a die, a 6-sided die. Let E, or we know what we can call it A, let A be the event that you flip a heads on the coin. Let B be the event that you roll a 5 on the die. Well, if you're kind of flipping the coin and rolling the die kind of not near each other, not all up in each other's business, then these two things are independent. The coin toss should not affect the die roll and vice versa. It doesn't make sense. The two are completely independent of each other because why would flipping the coin have anything to do with the dice as long as you keep them a good space or distance from each other? So these are indeed independent events. We'll keep that in mind. If you do have two independent events, the probability that they'll both occur, the probability of A and B, you can actually just multiply their individual probabilities. You can multiply their individual probabilities. So let's look at this example problem. A US roulette wheel. If you've ever gone to a casino, you have probably seen roulette, either virtual roulette or a physical roulette table. It's that big spinny wheel that has black, red, and green on the wheel. There are 38 total slots on the wheel. 18 of them are black, 18 of them are red, and 2 of the slots are green. The ball can land on any slot with equal probability. What is the probability of red occurring on 2 consecutive plays? Well, the probability that red occurs on any single play is there's 18 spaces that are red out of 38 total spaces on the wheel. So the probability is 9 out of 19. It's 18 over 38, which reduces to 9 over 19 as a fraction. So the probability reduces to 9 over 19. That's just the probability of getting red on any one play of roulette. Now, whenever you play roulette, they put a little white ball onto the wheel and it randomly finds itself to one of the numbers out there. If you play for a second spin, they're just going to pick the ball up again. They're going to spin the wheel and then they're going to put the ball out there. So whatever the outcome was for the first spin, it should have no effect on the outcome of the second spin. So we would argue that in this roulette case, the 2 spins are indeed independent of each other. So the probability of getting a red on the first spin and a red on the second spin, which is what it means to get red on 2 consecutive plays, you just multiply their individual probabilities. You do 9 over 19 times 9 over 19. You do the math, that becomes the fraction 81 over 361, which is about 0.224 or a 22.4% chance. And there you have it. So the probability of getting 2 reds in a row on 2 consecutive plays is about 0.224. So independent events are really nice because you can just, to find the probability of 2 events both occurring, event 1 and event 2, you just multiply their individual probabilities. What if you have more than just 2 events? More than just 2 events. Let's say you have more than 2 events. Well, if they're all independent of each other, meaning any 2 of them you pick are independent, they don't affect each other's outcomes. So imagine someone, the mother of a family giving birth to children. If the mother gives birth to 9 total children, we can find the probability that all 9 of those children will be girls. Assuming there's roughly a 1/2 probability or a 1/2 chance of getting a girl in any one birth, the probability that you'll get 9 girls in a row, you multiply the number 1 or the fraction 1/2 9 total times. So 1/2 times 1/2 times 1/2, blah, blah, blah. That's the same. You could write it as an exponent, 1/2 to the 9th power. That'll give you 1 out of 512. A very low chance that all 9 babies are girls. But it is possible. What's interesting is that girls are slightly more likely to be born than boys are in a given birth. It's actually, they have a slight edge, just a little bit more than 1/2, but it's very, very, very minuscule, the difference. It's almost hard to tell or to see. So a 1 in 512 chance. Let's say you're talking about hurricanes. Now, this year has been an absolutely wild year for tropical storms and hurricanes in Florida. I don't know if you've seen it, but there have been a record number of these types of storms in Florida, which is not good. But it's still something we can model with some interest. Let's say that the probability Florida will be hit by a hurricane in a single year is 5 out of 19, which it actually seems like that probability is getting higher and higher. We seem to hear about it all the time. But we're going to assume that in any one year, whether or not Florida gets hit by a hurricane is going to be independent of it getting hit by a hurricane in the next year. In other words, you can't predict what's going to happen next year based on this year. It's just like you're resetting the stage. Now, maybe you could argue that's not quite true, but we're going to assume that it's true for the sake of argument here. So what is the probability that South Florida will be hit by a hurricane in 3 consecutive years? Well, in any one year, it's 5 over 19. For 3 years in a row, since they're all independent, we do 5 over 19 times 5 over 19 times 5 over 19. You do the math on that. 5 cubed is 125. 19 cubed is 6,859. You do the math on that, and it comes out to about 1.8%, 0.018. So there's only about a 1.8% chance that Florida will see a hurricane 3 years in a row in any given stretch of 3 years. To continue on with that idea, if the probability that Florida will be hit by a hurricane in any single year is 5 out of 19, what is the probability that Florida, South Florida specifically, will not be hit by a hurricane at any point in the next 10 years? We first need to find the probability that Florida will not be hit by a hurricane in any one year. If the probability is 5 over 19 that it will be hit by a hurricane in 1 year, then we do 1 minus, we take the complement rule, 1 minus 5 over 19, which is 14 over 19, or about 0.737. Then there's about a 73.7% chance that Florida will not be hit by a hurricane in any 1 year. Now, assuming independence, we're going to say that the probability of not being hit by a hurricane for 10 years in a row, you need to do 0.737 times 0.737 times 0.737. You need to multiply it to itself 10 total times. Thus, it's 0.737 to the 10th, which is about 0.047. So there's about a 4.7% chance that Florida will see 10 straight years without a hurricane. So not very likely. It's more likely you'll have at least one hurricane at one point in those 10 years, because that's just how it works in Florida. Now, we've talked about independent events. We've talked about independent events. Two events are dependent. They depend on each other if the occurrence of one of them has an effect on the probability of the other. So it's the exact opposite of being independent. Independent said that they did not affect each other. Dependent events, though, do affect each other. So let's look at some examples of this. Let's look at some examples of this. Let's take our previous example where we were drawing two cards from a deck. And let's change it to without replacement. This means after you draw your first card, you then draw the second card right after without doing anything special. So if there's replacement, then they're independent. If there's no replacement though, you're just drawing basically two cards right off the top. You could say you're drawing card one first, give it a moment, and then drawing card two. It's the same thing. These events now of drawing a jack on the first card, drawing a jack on the second card, these events are not independent anymore. They are dependent. The reason is that if you draw a jack on the first card, there's only 3 left in the deck out of 51 cards in the deck. So the probability of event F has changed based on what happened first. We've changed the nature of it, so now we do have dependent events. So you'll see dependent events if you're running a probability experiment like this, that's all in like a closed system, like a single deck of cards. If you want a sad example, and so I use blue because blue is sad. When you look at older couples, people who have been together, 40, 50 years, and they're a bit older, when you look at older couples that have been together for a while, you find that when one of them dies, the other one dies shortly thereafter. Not always, but the probability that the second one will die suddenly increases. So normally a given person, even if they're older, the probability that they're going to die in the next year is not horribly too high, especially if they're younger. As they get older, that probability certainly goes up. But if they're, if they're with someone, they're married or whatever, and one of them does pass away, the second one, sadly, just kind of doesn't see a point in living anymore, or is ready to go, ready to meet their maker, whatever you want to call it. And that is a phenomenon we have noticed. And so that second person, their probability of dying in the next year, right after they lose their partner, is much, much higher than it normally would be. So it's not guaranteed that they will die. It's just saying it's more likely that they will die shortly after their partner. We see that happens all the time. You look at nursing homes, that happens all the time. Anyone will tell you that. It's possible if that second person, once their partner dies, if they do have a reason to live or if they want to continue living, maybe they have kids, grandkids, great-grandkids, someone, something that keeps them going even though they've lost their partner. Physically, from a health perspective, they may be able to continue on living for 5, 10 more years, 15, 20, who knows? It's just that, their heart may not be in it. And so if they do get sick, they may not fight it off, they might just kind of let themselves go. And while that is sad, that is a great example of dependent events. Thus, if you have E, that is the probability that someone will die, and F being the event, the probability that E's partner or husband or wife will live for another year. These are dependent. F definitely depends on E. So, some good examples here of dependent events. So, if two events now are dependent, you can't just multiply each of their individual probabilities. You have to make an adjustment based on what has occurred, based on what's already gone down and how it's affected the second probability. So let's look at a neat example. You have won a free trip to Madrid, maybe not in 2020, maybe not even in 2021, because I don't think anyone's flying or doing too much of that, but maybe you could. You've won a free trip to Madrid, and you can take 2 people with you, all expenses paid. The bad news is that 10 of your cousins have appeared out of nowhere and are begging you to take them. So yeah, maybe they normally don't reach out to you, but they're like, hey, maybe I can go to Spain for free and go see, cool stuff. So they're begging for you to take them. So here's what you're going to do. You're not going to just pick your favorite cousin, which is what I would do, or your favorite 2 cousins. What you would like to do, you can either pick your favorite cousin, or you might like to pick a cousin that speaks Spanish. If you're going to a Spanish-speaking country, that might be a pretty darn useful person to have on that trip. So here's what you're going to do. You write each cousin's name on a card, place the cards in a hat, and you're going to select one name. Then you're going to select a second name without replacing the first card. So you're going to select 2 people to come with you, as the problem states. Of your 10 cousins, 3 out of them speak Spanish. Let's find the probability that you will select 2 Spanish-speaking cousins. So let's go here. You have 10 cousins, 3 speak Spanish. If you randomly select 2 of these cousins, what is the probability that they will both speak Spanish? So here's what we want. We want the probability that cousin 1 speaks Spanish and we want the probability that cousin 2 speaks Spanish. These are dependent events because once you've picked your first cousin, it changes the probability setting for your second cousin. You've picked your first cousin. Now, instead of having 10 names still in the hat, now you only have 9 names in the hat. So this is going to be equal to the probability that cousin 1 speaks Spanish times according to that formula, times the probability that cousin 2 speaks Spanish given or knowing that cousin 1 speaks Spanish. Not speaks Spanish, speaks Spanish. The word given or assuming or under the condition at, we often in mathematics just use a vertical bar for that. Where am I getting that formula? How do I know it's that? Because I'm looking at the probability definition for dependent events, finding the and probability. The probability of A and B is equal to the probability of A times the probability of B, given that A has already occurred. That formula, again, is provided to you on the exam. This is going to end up being a lot easier than it looks. First off, the probability that cousin one speaks Spanish. You've got 10 names in the hat. You shake it up. 3 of the people in that hat speak Spanish, so there's a 3/10 chance that your first cousin that you select will speak Spanish. Times, now the probability cousin 2 speaks Spanish. If the hat were reset, if the hat were back to having all 10 names in it, this would not be any different. However, think about it. We're assuming that the first cousin, when we already selected, speaks Spanish. That means out of the 3 Spanish speakers in the hat, we've already chosen one. Then there's only 9 total names in the hat. So there's only a 2 out of 9 chance that cousin 2 will speak Spanish, given that cousin 1 already speaks Spanish, because we've already taken cousin 1 out of the hat who speaks Spanish. And we multiply those probabilities. So it's going to be 6 over 90, 1 out of 15, or about a 6.67% chance. So not a very good chance that I end up selecting 2 cousins that both speak Spanish. There's a possibility that I get 1 that speaks Spanish. That would still be useful. There's also a possibility that I select 2 cousins, neither of whom speak Spanish. And that would not be very good. If it was me, I would just take my cousins that spoke Spanish and say sorry to the rest of them. Unless I spoke Spanish myself, then I would just take my 2 favorite cousins. So there you go. If you're talking about more than one event, let's see. 3 people are randomly selected, 1 person at a time, from a group of 5 freshmen, 2 sophomores, and 4 juniors. There are no seniors in this group. So it looks like there's 11 total people in the group. 5 plus 2 plus 4 is 11. Find the probability that the first 2 people selected are freshmen and the third is a junior. So find the probability that the first 2 people are freshmen. So it's going to be conditional. There's 3 total stages. We want first the probability that the first one is a freshman. Then we need to update and find the probability that the second person is a freshman, given that a freshman was selected first. Finally, we need to then multiply by the probability that the third person is a junior, given that 2 freshmen have already been taken. So the probability of a freshman in the first case is 5 over 11. The probability of a freshman in the second case, well, 1 of the 5 freshmen have already been taken out, leaving me 4. 1 of the 11 people, period, have already been taken out, leaving me 10. So it's 5 over 11 times 4 out of 10. Finally, the junior, all 4 of the juniors are left here, but out of only 9 people. And so we multiply each of these probabilities together. Whatever the fraction becomes, it looks like it's 80 over 990, if you multiply that out exactly as you see it. 80 over 990, which just reduces to the fraction 8 out of 99. Eight over 99 is our final answer. It's the probability here. So pretty straightforward. Oops. So next up, we can actually talk about this whole probability of one event given that the other event has already occurred. We can actually talk about this. This is actually just in general called or referred to as conditional probability. We call that conditional probability because now we're placing a condition on things. So the probability of some event B given or assuming that some other event A has already occurred, that's called the conditional probability of B given A. And this is written probability of B, vertical bar means given A, the probability of B given A. This is how we take into account the possibility of one event affecting the probabilities of another. So conditional probability is going to be talked about in terms of dependent events. We're going to care about it when it's dependent events. So let's look at some examples of this. A letter is randomly selected from the letters of the English alphabet. Find the probability of selecting a vowel given that the outcome is a letter that precedes H. So here's what we're doing. Let me explain it better than this. We are selecting a letter of the alphabet at random. We want to know the probability that the letter is a vowel. Your vowels are A, E, I, O, U. If I tell you beforehand, I don't tell you what the letter is, but I say, if I tell you beforehand that the letter you drew comes before H, what is the probability of a vowel then? So let's define two events. A is the event that the letter comes before H. That the letter you just drew, even though you haven't looked at it yet, I can tell you that it comes before H. Let's let B be the event that the letter is a vowel. So then the probability of B given A, this is what we want. We want the probability that of B that the letter is a vowel given that the letter comes before H in the alphabet. The letters that come before H, let's write it out as a set. A, B, C, D, E, F, G. So basically what I'm telling you is you're drawing a letter from the alphabet. I'm telling you the letter is either A, B, C, D, E, F, or G. It's one of those letters only, not any of the 26. So now that I've supplied you with some new information, it completely updates the probability. It completely changes how likely you are to get, that letter of the alphabet. So let's see. We know it's got to be one of these letters. There's 1, 2, 3, 4, 5, 6, 7. There are 7 letters of the alphabet that come before H. And 2 of them, A and E, are vowels. So there's a 2/7 chance, whatever that converts to as a decimal or a percent, there's a 2/7 chance that the letter you draw will be a vowel once you know that it has to come before H. Basically, by me telling you that the letter came before H, I've zoomed into the possibilities, and there's only 7 now. That's why it changes the probabilities. If I didn't put this given A business on here, if I just wanted the probability of B, I just wanted the probability that the letter is a vowel, that would be 5 out of 26, a 5/26 chance. But since I've supplied you with different information, it completely changes it. It changes the probability entirely. That's how conditional probability works. We can look at conditional probabilities with real world data. Let's say we randomly found a random sample of 100,000 US women between the ages of 50 and 60. A mammogram is a medical test that is done to detect breast cancer. It is strongly suggested, especially I think when you hit the age of like 35 or 40, if you're a woman, it's strongly suggested that you have a mammogram every single year. Because if you do happen to have breast cancer, the more often you're testing for it, the earlier you can catch it. And if you can catch breast cancer very early, it has a much lower chance of causing serious problems. So obviously cancer is nothing to joke about. It's not funny. Go and get tested. If you think you have something, try and figure out what it is and, start treating it as soon as you can if it is something bad. At any rate, out of the 100,000 women that we took the sample data for, 720 of them had breast cancer and a positive mammogram. Now that sounds weird. But what will happen is that these machines are not perfect. These things that we use to test for breast cancer, even COVID-19 tests, they're getting better and better, but some of the early ones were not foolproof by any stretch. So what happens is 7,664 of these women came back with a positive mammogram, meaning that it came back and said you might have breast cancer. But only 720 of the women out of that group actually do have breast cancer. 6,944 of them tested positive for it, but don't actually have breast cancer. And that's because a mammogram is not perfect. Usually what they'll have you do is if they get a positive result on a mammogram, they will have you take several and they'll do other tests to confirm that you have breast cancer. Then 92,336 of the 100,000 women came back and their mammogram said was negative, that they did not have breast cancer. In truth, though, 80 of those women still do have breast cancer. That's called a false negative. You have false positives and false negatives. A test designed to detect things like that is considered a good test if it has a very low false positive rate and a very low false negative rate. And it's usually very hard to get both of those in line. False positives are actually not as bad. A false positive is okay because you might freak out for a second, but they're going to suggest we do several things to see if you have breast cancer. You take several mammograms. So it's a high false positive rate isn't the end of the world, though you still want it to be accurate. A high false negative rate is really what's bad, because if it's very likely that you come back, you get a negative result on the mammogram, but you really do have breast cancer, that might give you a false sense of peace when you should be getting it treated. So a high false positive rate is not a big deal. A high false negative rate is a problem, a huge problem. But at any rate, let's find the probability that a woman, one of these 100,000 women, has a positive mammogram given that she does not have breast cancer. Well, it's given that she doesn't have breast cancer. So we are looking only at this column. We are looking only at this column. We're only looking because it's given, it's told to us. We have been told that this woman does not have breast cancer. Whatever woman we randomly select, we're told she doesn't have breast cancer. We just want to know the probability that she will test positive for breast cancer, even though she doesn't actually have it. So we look at, of the 99,200 that do not have breast cancer, we take the 6,944 that do have breast cancer, and we take a proportion. We say 6944 out of the 99,200. We don't divide by 100,000 because we're only looking at the women that we know do not have breast cancer. How do we know that? Unfortunately, the answer for now is just that it's kind of magic. We just magically know. And so there's a 0.07, exactly 0.07, or a 7% chance that if you don't have breast cancer, you'll still test positive for it on a mammogram. Among this group, there's a 7% chance that a woman will test positive on the mammogram, even though she doesn't have the breast cancer. That would be the false positive rate. 7% of positive, well, something like that. And so we see, there you go, 0.07. So that's kind of interesting. There's 99,200 that don't, but 7% of the women who don't have breast cancer will test positive for it. Kind of wild. A proper test is a woman who has breast cancer and the mammogram comes back positive. While that's not good news, that's at least the test was performed correctly. Another correct test would be your test comes back and is negative and you don't have breast cancer. That's correct. We want that to happen. We don't want these two squares to happen. These are bad, especially this one. Okay, let me pull up our next set. Here, we'll start it real quick. Here we are. For the last section of chapter 11 here, we're going to talk about something called expected value. Expected value. This is a pretty important concept in statistics for several reasons. The biggest reason is the expected value is kind of like the average value. In fact, it is exactly the average value. Now, if you have a whole set of numbers and you want to take their average, you just add up all the numbers and divide by how many you have. However, if those numbers each have different probabilities of occurring, if we add them all up and divide by how many we have, we're assuming they're all equally likely to happen. But in reality, if some values are more likely to happen than others, we want them to have more weight. We want them to be more affecting the average. So the expected value kind of gives us the average while taking in the probabilities of each individual state. And that's what we want. That is preferable. So expected value is a mathematical way to use probabilities to determine what to expect in various situations in the long run. Expected value is used to determine premiums on insurance policies. When you pay for insurance, you're paying what is called a premium. Now, here's what the insurance company is doing. Let's say your insurance is $100 a month for your car, so you're paying $1,200 a year for car insurance. Your insurance company might calculate the expected value that it's going to cost them to pay for damages to you and your car if you get in any accidents this year. So the idea is the insurance company expects to have to shell out about $1,000 for you this year. Even if you don't end up getting in a car accident, they're trying to predict the future and they don't know that that's going to happen. So they expect that you're going to cost them $1,000 this year. So if they charge you a premium of $1,200 for a year, they're going to cover that expected cost and pull a nice little profit. Now, obviously, it's a lot more complicated than that, but that's the basic idea behind it. So they look at what they expect you to cost them this year, and if they charge the same, they'll break even. So they got to charge a little more because they have employees to pay. They have profits that have to be made, stockholders, shareholders, things like that that they have to report to. What it can also do is it can weigh the risk versus benefits in several alternatives in business ventures. So if you're a company, you sit down, you're like, we can invest this money in 4 different things. You might look at which one has the highest expected return. It's not guaranteed to return that much money. It's just expected. You also want to look at what will happen if you continue to play a game of chance in the long run. So a casino will look at expected value. The casino says, on average, the player will lose $1 every hand of blackjack where they play $10. So it's possible that a player wins and beats the house and makes money, but it's more likely, it's expected that they'll actually lose money per hand of blackjack they play, and thus that's a profit to the casino. The way we're going to compute expected value, you multiply each numerical outcome of a probability distribution by its probability and then add these products all together. So we will look at a computation of this in just a moment. We'll also look at some interesting ones. Let's take attendance. And the standard way to compute expected value, look, there's this magical special formula that involves a giant capital sigma, the letter from Greek, the Greek alphabet. But it's just kind of ugly looking. So the general formula for computing expected value is to take each numerical outcome of something and multiply by its probability. Then you add up all of these products that you found. So let's find the expected value for the number of girls for a family with 3 children. This one is an interesting one. So basically, if you have 3 children, how many of them do you expect to be girls? And how many do you expect to be boys? You're going to find the expected value will be a number that is impossible. It's going to end up being 1.5. You can't have 1.5 girls. So the expected value, it's not about what's going to happen. It's the best guess you have for what will happen. But it's usually not going to be a possible value. So let's see, if you have 3 children, there's 4 possibilities. You can have 0 girls, you can have 1 girl, 2 girls, or 3 girls. But to compute the probability of each of those, there's 8 possible outcomes. You can do boy, 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 girl, boy, 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 girl, boy, 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 girl, 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 boy, girl, boy, girl, boy, girl, girl, and then finally all 3 girls, girl, girl, girl. So there's 8 possible outcomes. One of the 8 possible outcomes yields 0 girls. 3 of the 8 possible outcomes yields exactly 1 girl. 3 of the 8 possible outcomes yields exactly 2 girls. And then 1 of the 8 possible outcomes yields 3 girls. Thus, when we're talking about probability, the probability of getting 0 girls is the one way it can happen divided by the 8 total outcomes that are possible. The probability of getting 1 girl, exactly 1 girl, there's 3 ways you can get 1 girl out of the 8 possible ways. There's 3 ways you can get 2 girls out of the 8 total possible outcomes. And there's 1 way you can get 3 girls out of the 8 total possible outcomes. So we take 0 girls times 1/8, the probability of getting 0 girls, plus 1 times 3/8, 1 girl times the probability of getting 1 girl, which is 3/8, plus 2 times 3/8, 2 girls times the probability of getting 2 girls, which is 3/8, plus 3 times 1/8, the outcome of getting 3 girls times the probability of getting 3 girls, which is 1/8. This is how we do expected value. It's kind of a pain in the butt. Of course, you have calculators. You have calculators where you can use parentheses. You can do all this calculation in one line. Let me show you exactly how I would do this calculation in one line on a calculator, you could literally do 0 times 1/8 in parentheses plus 1 times 3/8. You don't even have to do spaces before your plus because you can't do spaces in a calculator per se. Plus 2 times 3/8 plus 3 times 1/8. Now your calculator might give it to you as the fraction 3/2. It might calculate that as 3/2. You just need to know to do 3 divided by 2, which is 1.5. So it looks like I predicted the answer correctly. Is it because I'm a super genius? No, it's because I knew the probability structure was symmetric. It's 1, then 3/8, then 3/8 again, then 1/8. So kind of interesting. So what does that mean? 1.5 girls. Again, a single family can't literally have 1.5 girls. But if I took thousands of families that had 3 children, then on average, there's going to be 1.5 girls per family. Again, not possible for any one of them, but as an average, it is. You know, this person, oh, this family has 0 girls. Oh, this family has 2 girls. This next family has 2 girls. This next person has 1 girl. This next family has 2 girls. This next family has 3 girls. This next family has 2 girls. If I keep adding up those numbers, 0 plus 1 plus 2 plus 2 plus 3 plus 1 plus 0 plus 2 plus 2, the number of girls all those families have, and then I divide by the number of families, I'm going to be hovering near 1.5. So the average isn't always something that can literally occur. It's just an idea. It gives you an idea that on average, a family will have between 1 and 2 girls if they have 3 children. So you just have to interpret the expected value appropriately. Next up, let's talk about insurance. Let's talk about insurance. If you drive a car, you have insurance. If you're driving a car without insurance, you're technically breaking the law. Now, you might just get a ticket from a police officer if that's the case, but you do need to have insurance if you're driving. At least liability insurance, which covers the other person if you cause the accident, which is just right and proper, isn't it? If you cause an accident, you should pay for the other person's damages. But anyways, an automobile insurance company has determined the probabilities for different claim amounts. So let's say if you're a driver between the ages of 16 and 21, some of you out there might just be that. That frankly is your youngest people. And you know, the insurance company thinks that you are just the devil and thinks that you are going to get into an accident, but not completely. So when you make a claim to your insurance company, if you claim $4,000, that means the insurance company, if your claim is accepted, your insurance company has to shell out $4,000 to fix your car, to fix the car or property that you damaged. So the insurance company says that there's a 70% chance, a 0.7 chance, that for as an individual driver between 16 and 21, the insurance company is going to have to shell out $0 in claim. So the insurance company actually thinks it's likely that they won't need to pay for you at all. They won't need to pay anything. There's a 15% chance, the insurance company believes, there's a 15% chance that you're going to cost them $2,000 in claim damage this year. There's an 8% chance that you're going to cost them $4,000. There's a 5% chance, 0.05 chance, you're going to cost them $6,000, a 1% chance you'll cost them $8,000, and a 1% chance you'll call them $10,000. It is really nice to put each of the possible outcomes right here in a table next to their probability. That makes it really easy to do this expected value computation. You literally take the claim amount times the probability, 0 times 0.7, plus 2,000 times 0.15. Oh, look, they're doing it right here. Take each claim amount, take each numerical outcome, multiply by its probability, and add all these bad boys up. Remember your order of operations. You multiply in each case first before you do any of the addition. You'll end up with 0 plus 300 plus 320 Now, this 320 doesn't mean anything by itself per se. It's just part of the calculation to get the entire expected value. So 0 plus 300 plus 320 plus 300 plus 80 plus 100. The insurance company believes that on average, a driver between the ages of 16 and 21 is going to cost them $1,100 in a year. Most of the drivers, it will not cost them anything, but the ones who are getting into accidents, they are raising up the average. So if the insurance company charges a driver between the ages of 16 and 21, if they charge that driver $1,100 for the year, which comes out to a little bit under $100 a month, like 90 something bucks a month, then the insurance company will break even. They will not profit off that person, but they will not lose money either. Now think about it. The $1,100 that we just computed isn't one of the possible outcomes. So the $1,100 on its own is not something that can happen. You're either going to cost 0, 2,000, 4,000, 6,000, 8,000, or 10,000 to the insurance company. Those are the only possibilities. Of course, in reality, there's far more than that. But the idea behind the 1,100 is that if the insurance company looked at many policies, thousands of insurance policies for drivers between 16 and 21, on average, among all those policies, the insurance company lost $1,100 in claims that they had to pay for you or for those people getting in accidents or whatever. So if the insurance company charged that person $1,100, they break even on average. But if one person did cost them $10,000, but only paid $1,100 in premium, that person profited $8,900 if you think about it. But there's other people who aren't getting into accidents that are helping cover their premium. That's the idea behind insurance, if you want a real simple case. So in reality, they might charge you $1,100. That's if they break even. In reality, they're going to charge you something more like $1,400 or $1,500 a year so that they can pull a profit. Because now, if they charge $1,500 a year and only expect to shell out $1,100, they're going to, on average, profit $400 per person per year. And insurance companies, they're a company. They have to pull a profit. You're not going to go into business and give away things for free for too long if you're opening your own, your Etsy business. So insurance companies are not evil for requiring a profit. I mean, those are jobs. The profit is being used to pay employees. And so that's creating jobs for people. Things like that. Where expected value really shines is in games of chance, which, games of chance are the best. They're fun. You think about loot crates on video games. If you play video games and you're playing the new Call of Duty Brawl and, you go on a whatever streak or you win 3 games in a row or something like that, the game might reward you with a loot crate and you can open it up and it'll randomly assign, you'll get this new pair of sunglasses for your in-game character so you can change your aesthetic. Oh, you'll get these new parts for guns. A loot crate is a game of chance. There's a probability that you'll get this item. Then there's a probability you'll get this item, a probability you'll get this item, and so on. So let's say that you are playing roulette. You're playing roulette. Find the expected value of betting $1 on the number 20 in roulette. So if you were to bet $1 on the number 20, and then they spin the roulette wheel and it lands on 20 exactly. So we're not talking about red, black, and green. We're talking about the number itself. If you guess the number completely correctly, you're going to win $35, which is pretty cool. If you guess the number incorrectly, you lose your dollar bet. So you're down $1. So we would literally represent a loss with a negative number. We'd say negative $1 were earned here. Well, that's interesting. Because there are 38 total slots, it turns out you're going to need to win $38 on average to really make up for it. Instead, you're only winning $35. So the casino has what we call an edge here. So let's think about it. If the ball lands on that 20, your total net gain, you not only get your dollar back that you bet, but we're not calling that a gain. We're just saying you're not losing your dollar. The real gain is you win $35. It's a little confusing because now you'll have $36 in your hand, but only 35 of them were winnings. So your net winnings are $35 with a probability of 1 out of 38. However, if the ball does not land on 20, you lose $1, and that's going to happen almost certainly with a 37/38 chance. Just 37 of the spaces on roulette go against you. So we take each thing, we take the 35, we multiply by its probability. We take the negative one and make sure it's negative. You're adding -1, which is fine. You do that, and you multiply it by 37/38. These could be seen as fractions. This becomes the fraction 35/38, essentially minus 37/38. So just for simplicity, they just brought it into the same fraction. The fraction ends up being -2/38, which reduces to -0.05. So playing roulette is bad. The expected winnings are actually negative. So if I go and I play this roulette where I'm just constantly picking a number and hoping the ball lands on that exact number, on average, I will lose 5 cents every time I bet. It's impossible for me to actually lose 5 cents. There's only two possibilities. I either lose $1 or I gain 35. Those are the only two possibilities. There's no way I'm going to lose exactly 5 cents. What's it saying is if I keep playing this game over and over and over, if I played it thousands of times, I'm going to, on average, lose 5 cents each time I play the game, which in turn means the casino is going to be making 5 cents every time I play. You're going to find that every game in a casino has this setup where your expected winnings are negative. Your expected winnings are negative on any one play of it. But it's a probability game. What if you go in, you put $1 down on roulette? Heck, let's say you put $300 down on roulette on the number 20. You do that, and the ball comes up the number 20. You get $35 for every $1 you put down. You put down $300. So 300 times 35, you would make what, $10,500? So you just won $10,500. First of all, walk away, baby. Walk away right now. Don't think you're going to keep doing it. Oh, I could put that means I could put $5,000 on the next turn. No, just because you just won at roulette, they're independent events. The next turn, it has no guarantee it's going your way. The next turn is a fresh, new state of nature. So it's possible you walk in there, you put $300 down, you win $10,500, then you go eat at their nice fancy steakhouse they have. You go watch a show, maybe a magic show at the casino. You plan to do some more gambling, but you already won a ton of money, so you just have a little bit of fun at the casino the rest of the weekend. That's possible, but it's not likely. Instead, what's more likely is you put the $300 down, you lose. You try again, put another $300 down, you lose. You try again, you lose. Maybe you play it 50 total times and you only win one of those times. Now that one win is nice, but the other 49 losses actually end up being worse than that one win in total, which means in total you lose money in that situation. So casinos are fine if a couple people here and there are winning money and walk out winners, because the amount of people losing money and walking out with less money than they walked in with is so much higher. In the long run, the casino will profit, guaranteed. If you're curious, I believe the only primary game at a casino that you have an even chance with the house, you're 50-50, is craps. So if you keep playing craps, which is dice, you're tossing dice, and you bet properly. So in other words, you actually know how to play craps. You don't just walk in and do whatever. If you keep playing craps and you know what you're doing, in the long run, you won't win anything, but you won't lose anything. You'll break even with the casino. That's like the only game the casino does that. The reason the casinos will have it is because it's a popular game, and they're hoping that if you come in to play craps, you might play on their slots, or you might play their blackjack or roulette and lose money somewhere else and lose all that money. So craps, I believe, is the only game that you have an even shot with the casino. or that your expected value is 0. Ideally, you would play a game where your expected value was positive. But anyone who's smart enough that puts up a game like that is not going to let you have a positive expected value. Think about the lottery. If you think about the the state lottery, I think I mentioned it last time, but if the state lottery is giving out $1.5 billion, it's the Powerball to whoever wins. 1.5 billion is a lot of money, but what if that state lottery raises $2 billion from the sales of their lottery tickets? That means even though the state has to shell out 1.5 billion, they're making 2 billion, so they're profiting $500 million. That's what the lottery is. The lottery is a giant game of chance played like that, where the state expects for more lottery tickets to be sold and the total revenue brought in to be higher than what they have to pay out. So the state profits. And when I say state, I mean the state government. So that's kind of wild. Okay, so that was it for chapter 11. And now we're ready to jump into chapter 12. This is the last chapter we cover in this course. Chapter 12 is a crash course in statistics. Technically, so is chapter 11, because it turns out probability theory is like the language of statistics. You cannot do anything in statistics without probability theory. Josh, I don't believe you. Well, it just so happens I actually got my master's degree in statistics. I had a focus on statistics. So statistics is very importantly entrenched with probability theory. It may not appear to be at first, but you're going to see how it will. So the general definition. So unfortunately, this section is going to be a little bit of just kind of definitions and learning new vocabulary. It's not perhaps quite as interesting. We may not see as many numbers pop up. Statistics is the science. It is the science of collecting, organizing, analyzing, interpreting data. Yeah, statistics is entirely concerned with data. Data is the most important thing, not the android from Star Trek: The Next Generation. We break statistics into two branches. There's the boring branch called descriptive statistics, where we just kind of collect, organize, summarize, and present data, perhaps in charts or tables, make visualizations of it, pie charts, graphs. It's not as fun. It's important, though. You have to know how to take the average of a set of data, standard deviation, all those numerical things. But it is just not fun. It's just like, you're putting it into a computer and whatever. That's the boring side. The fun side, and I'm using the fun loosely because maybe you don't think math is fun. The fun side is inferential statistics, where you actually take that data and you draw inference about the population from it. You actually do something with it. So we look at two concepts. We look at the population. This is the set containing all the people or objects whose properties we are trying to describe and understand and analyze. The population, it could be the US population, it could be the world population, which is over 7 billion, possibly even 8 or 9, 10 billion, who knows? You could be talking about the population of all iPhone 8s or iPhone 12s, I think is the current one. So it can be people or objects, it just depends on the context. But the population is everything of interest to you. A sample is going to be a subgroup or a subset of the population. It's going to be some piece of it, but not the whole thing. A representative sample, which is what we want in statistics. This is a sample where even though it's only a small portion of the entire population, it still, on average, exhibits the characteristics typical of the entire population. That's good. That's good. You want a representative sample. But statistics is all about whether or not you can actually get one of those, how you determine if one is good. So let's look at a few examples. A group of hotel owners in a large city decide to conduct a survey among citizens to decide what their opinion is on casino gambling. Because maybe the hotels are deciding maybe we'll open some casinos in our hotels. We got all these conference rooms that we're not using. Let's convert them into casinos. But you might have to make sure that's cool with the people around. The population is going to be all the citizens in that city, whatever that large city is. Detroit, New York. I'm not going to attempt to do any accents. Now, one of the hotel owners says, look, whoa, there's 10 million people in this city. Maybe you're in LA or New York. 10 million people in a city? That's way too many people for me to run a survey on. You're not going to get 10 million people to respond to you. So here's what we're going to do instead. The hotel owner suggests obtaining a sample by surveying all the people at 6 of the largest nightclubs in the city on a Saturday night. Now, I will bet you $500 if you're hanging out at a nightclub, you're doing things at a nightclub, I bet you are not going to want to talk to some nerdy guy or gal who, is like, will you answer my survey? But maybe if they offer to buy some drinks or something, you get a free drink at this bar if you answer this survey. But anyways, let's assume this is even feasible. Each person will be asked to express their opinion on casino gambling. Is this a good idea? So the sample is just all the people at 6 nightclubs on a Saturday night. Do you think that's a good representation of the population? No. Maybe it is. It just depends. The thing is, the nightclub people they're more likely to be the kind of people that would go to a casino. Not that there's anything wrong with either. I love going to casinos. Nightclubs just give me anxiety, to be honest. I'm like, oh, it's so loud and the lights are everywhere and everyone's, acting a fool. I'd rather just stay at home and play Minecraft. All right. But you would expect people who are willing to go to a nightclub to also probably be cool with going to a casino or being cool with gambling becoming legal in that city. So it's a terrible, terrible, horrible idea because you're only talking to the yes men, the people who are going to say, yeah, that's cool. In reality, it could turn out, no, the majority of everyone in the city doesn't actually want a casino. What you've done is you've introduced a considerable amount of bias. Bias, B-I-A-S, is anything that could possibly make your sample not a good representation of the population. It's anything that makes you miss your mark. And again, don't get me wrong, I love going to casinos. Before the pandemic, WinStar was a lot of fun. Oh, I loved WinStar. Now I get, 10 emails a week. They're like, we'll give you 3 free weeks at our hotel. We'll give you, a free buffet every night. Please come to WinStar and gamble, please. So hopefully WinStar survives the pandemic. I bet casino gambling in Texas won't happen for a long time. So you have to go up to Oklahoma or Louisiana. So more concepts. A random sample is a sample obtained in such a way that every element in the population has an equal chance of being selected for the sample. Boom, I just read that word for word, but did I look at the screen? No, because that is the classic definition of what a random sample is. It's one where anybody in the population can make it in. You look at this nightclub example, every person in the entire population of that city is not equally likely to make it into your sample, only the ones who chose to go out to the nightclubs on Saturday. So that's why that's not a random sample. A random sample instead says everybody has a chance of making it in. That's what we want. We want random sampling. That's the best we can do. It may not be perfect. We may not even know how good it is for a specific sample, but it's the best we can do. A few ways you could do that. You could take, if you had a list of everyone who lived in the city of 10 million people, somehow you had that list, you assign all of them a number, and then if you want a sample of 1,000, you just pick 1,000 random numbers between 1 and 10 million. You go find who corresponded to the numbers selected, and boom. Think about combinations and permutations. If you had 10 million people and you wanted to select 1,000 of them, and you don't care about the order of the group once you get it, the sample, there's 10 million C1000 different samples you could pull. And I know what you're thinking. Go try it in your calculator, and your calculator will scream at you. Go ahead and try it. Try it in your calculator. 10 million C or NCR 1000. That's how many different samples you could possibly take from this city. Your calculator is going to scream at you and say, no, 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 I'm not doing that. All right, no, I'm not doing that. There probably is even just, they won't even try to calculate it. Yeah, if you do 10 million C 1000. It says error, yeah. There isn't, that whatever that number is, it is a number, but I'll bet you it's one of those just hilariously, ridiculously massive numbers. Yeah, you can't even begin to count how large that number is. It's like ridiculous. So, you know, in theory, if you had a population of 10 and you want to take a sample of 3, you could do 10C3, and that's how many samples are possible, and that would be a reasonable number. But once you start talking about major population sizes, that just becomes ridiculous. So, which of the following is the best way to select a random sample to decide how the city's citizens feel about casino gambling? Randomly survey people who live in the oceanfront condominiums in the city. Oh, so they get to live right on the beach and they can go out to the beach whenever they feel like. They don't have to drive anywhere. They just go right out there and they lay out their towel. Well, no, that doesn't characterize everyone. I mean, these are people who are living the Matthew McConaughey lifestyle. We have no idea if that's a good sample of the population. In fact, I would guess that it's not. So that's not random sampling. Geography like that. Maybe you survey the first 200 people whose name appear in the city's telephone directory. That's not exactly random sampling because, you know, that's mostly going to be people with A last names. That's not quite going to do it. But maybe if you randomly select neighborhoods of the city and then randomly survey people within the neighborhoods, you're getting better. You're getting better at it. That should give every citizen in the city an equal chance of making it into your sample. Actually, that's not, you could argue that that is the case, yeah. That might be, that's kind of a form of cluster sampling, you might call it. Okay, so now we are going to jump. We're talking about some of the basics of statistics. We can also talk about something called a frequency distribution. And kind of the best way to talk about a frequency distribution is to just do it. Just jump in. Jump in. So what we're going to do, we're going to construct a frequency distribution for the data of the age of maximum yearly growth for 35 boys. So we have 35 different boys, a sample of 35 of them, and we ask them, what age were you when you grew the most that you ever have in your entire life? Looks like you have a 10-year-old who grew a whole bunch when they were 10 and never quite grew up as much later on. You have some 11-year-old boys, you got some 12-year-old boys, 13-year-olds, 14-year-olds. This is just saying the way the data is splayed out like this. This is saying, all right, the first boy was 12, the second boy was 14, the third boy was 13, the fourth boy was 14, the fifth boy was 16, and so on. So a frequency distribution, you would have these things called classes. These are classes that each of the numbers could belong in. So the numbers range from 10 to 18. So this frequency distribution does classes for each one of the years between 10 and 18. Then the frequency is how many fell into that class. How many 10-year-old boys were there in this list? Just one. How many 11-year-olds were there? Well, here's one, 2 total. How many 12-year-olds were there? 5. How many 13-year-olds were there? 7. How many 14-year-olds were there? 9. You just got to count from the data. And we can see that the bulk of the data clusters between like 12 and 15, which that sounds about right. That's puberty, usually for boys. So a frequency distribution is not anything that's too horribly complicated. So yeah, maximum growth, most subjects occurred between the ages of 12 and 15. It keeps going up until you hit about 14, and then it slowly goes down after that. Let's look at a statistics test. Say you're in a statistics class, and 40 students are in the class, so 40 people just took a recent exam. The first person scored an 82. The second person scored a 47. The third person a 75, then a 64, and so on. So here's the 40 scores for 40 students. What we can do, we can group this into classes that are meaningful. What do I mean by that? Well, I mean we group them in a way that makes sense. Here, we don't want to group them by, okay, the lowest score is I see a 43 in there. The highest score is like a 99 or something like that, 94. So, all right, this frequency chart, I'm not going to do 47, 48, 49, 50, 51, 52, and then put the frequencies in each. Instead, for this one, I'm going to group them together by something that's logical, the tens. People who scored 40 to 49, people who scored 50 to 59, people who scored in the 60s, people who scored in the 70s, the 80s, and the 90s. So there were 3 people who scored in the 40s, 6 people in the 50s, and so on. These frequencies need to add up to 40, exactly 40, because we had 40 total data points. We have 40 different students taking the exam. So frequency distribution is not that bad. We can talk about something called the class width. The class width, how wide is each class here? You're tempted to say, oh, well, the class goes from 40 to 49. So 49 minus 40 is 9. You're tempted to say the class width is 9. That's not going to be the case. The class width is going to be the distance between 2 succeeding classes between their lower values. So it's actually the class width is found by doing 50 minus 40, or 60 minus 50, or 70 minus 60, whatever you want. The reason we do that is because if you think about it, the class width is counting up how many total possible scores could go there. And between 40 and 49, if you count on your hands, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49. Oh, there's 10 different values that could fall in that class width. So you're tempted to say it's 9, but really it's going to be 10 here. Then you can talk about the lower limit for the first class is 40. The upper limit for the fourth class, okay, 1, 2, 3, 4, upper limit 79. So frequency distributions are pretty gosh darn logical, if you ask me. Now let's go back and look at that chart for the boys. For the boys' growth, the ages at which they had their maximal growth. What we can do is we can make a histogram out of these. There was, so on the x-axis here, we're going to put the different ages. It's basically a bar chart where all the bars are touching. So there was one boy who grew the most at age 10, 2 boys who grew the most at age 11, 5 boys who grew the most at age 12. The height of the bar is going to be the frequency. It's going to be the number of things that went that way. So the bar for 10 is 1 high, the bar for 11 is 2 high, and so on. Then we can see from the histogram, because of where the heights of the bars are, we can see kind of the glut, the biggest part where it all falls. You can draw a frequency polygon, which is where you just connect the dots between the midpoints of the heights of each bar. And you can kind of see that it looks like a wizard hat. What's that one book series? They turn it into movies where the kids all go off to that magic school to learn how to become wizards and witches. Is a super popular movie series and book series too. The main character is named Harry Potter. He has friends Ron and Hermione. Dumbledore is the headmaster of this school of Hogwarts. I can't remember what the book series is called or the movie series, but if any of you can think about it, please share. Looks like someone did answer. Xavier said that the book series, the movie series are called Harry Potter, but that's the main character. you're not gonna name the movie series or the book series after the main character. It's got to be something else like Magic School or something like that. Obviously, I'm wearing a mask, so if you're in person, you can't see the giant smile on my face. You can't. Maybe you can hear the subtle, dry wit in the tone of my voice. Um, but yeah, nope. I'm a big fan of this book series and movie series, whatever it's called. Of course, that's because I'm a millennial, and every millennial loves it. So, anywho, what's popular with the Gen Z? What's like the Harry Potter of Gen Z? Is it and not like TikTok, but like a media franchise? Um, Star Wars has been popular for a while. Game of Thrones, not really. That's more a little older. I don't know. I'll have to think about that. What's the most popular? You guys can let me know your opinion. What's the most popular media franchise for you Gen Zers? Of course, who cares if we're a millennial or a Gen Z? We're all people. Let's just. I really hate when they do that. You kids don't understand what it was like growing up. Anyways, next up we can talk about the next thing are stem and leaf plots. Stem and leaf plots. These are kind of weird little plots that we can do. It's best to just look at some examples of them and it's going to make pretty much immediate sense. But what we're going to do is for the standard stem and leaf plot, you have these things called stems, which are the tens digits of the numbers you're dealing with. And then you have the leaves, which are the ones digits. So it's going to make perfect sense once you actually see one. Maybe you've seen one before. Here's that data we had for the 40 test takers who were taking that exam in statistics. The first person, whoever it is, alphabetically or otherwise, got an 82, then a 47, the next person a 75. The tens digits would be the 40s, 50s, 60s, 70s, 80s, and 90s. So in one column on the stem and leaf plot, we're going to put 40s, 4 for 40s, 5 for fighting, or 5 for 50s, 6 for 60s, and so on. The leaves, we're going to put the actual numbers there. So 82 would literally be 80 and the 8 over here, and then you need to put a 2 in the leaves column. 47 on the 4 stem, you need to have a 7 in there. That represents 47. So literally, this is the stem and leaf plot for those 40 data points. You'll count that there's 40 total leaves here, as there should be. This 7 is not the number 7, it's the number 47. This is the number 45. This is the number 43. Then 57, 54, 56, another 57, so you do put repeats in there. 50, 59, and so on. That's all the stem and leaf plot is. When you're constructing a stem and leaf plot, you want the spacing between numbers to be the same because the whole point of the stem and leaf plot is to see what is coming out to the right the most. And that way we can see what is the most commonly occurring values. So you can talk about stem and leaf plots like that. You've probably seen pie charts before. We just looked at histograms, which are just bar charts where the bars all connect so that we have a nice, smooth, flowing pattern. We can talk about deceptive practices or deceptive visuals. And this is where you can get really, really, sneaky here. You can lie. Let's look at the poverty rate in the US between 2001 and 2005. The poverty rate is the percent of people living in the US who are expected to be at or below the poverty line. The US has a specific definition for poverty. It changes every year. It's based on, I think, household income and also what region of the country you're in. Did you know that San Francisco, California, which has some, I think in the major San Francisco area, it has the highest property value, but also it's the highest cost of living is in San Francisco, not New York City, believe it or not, but in San Francisco. And the poverty line for a family of 4 is like something like $120,000, meaning that if you have a family of 4 living in San Francisco, and the household income is $120,000, that family is considered to be living in poverty. So poverty is not just based on how much money is being made, but also where you're living. That's ridiculous. If you lived in Texas, even though our property values are going up, cost of living is going up in Texas, a family of four living on 120K, that's a pretty darn good income for a household. $120,000 should be in Texas a really good amount of money to live on for a family of four. So just pretty wild if you think about it, that San Francisco is just that expensive to live there. And it's not even that nice. It's okay. It's a little chilly when it shouldn't be. It's a little chillier than the rest of California because it's on the water. It's okay. I like it. If you've ever been to the San Francisco Giants, the baseball team out there, their ballpark is incredible. I have not yet been to one. I've walked by it, and I want to go to a ball game there as soon as I can. It's on the waterfront, so you're watching a baseball game, and then you get to look out and see the ocean, and that would be the Pacific Ocean. Anyways, as I'm just rambling here, you're like, Mr. Gunther, please quit rambling. So I'll quit rambling. So in 2001, the U.S. poverty rate was 11.7%. So 11.7% of people were considered at or below the poverty level. They were considered, povertous, poor, very poor. And obviously that's not good. We want to get that poverty rate down. We want to lower it. It looks like it ticked up a little bit in 2002. It went up even more in 2003. It went up even more in 2004. And it dropped down a hair in 2005. These graphs can be very misleading. Look at this graph. If it's between 11.3% and 12.9%, oh my gosh, we're screaming, it's going up so much. It looks worse than it is. But jumping from 11.7% to 12.7% in 3 years, while that sounds bad, that's not horribly dramatic. It's not as dramatic as it looks from that graph. So the scale of your y-axis on some of these graphs, like this line graph, the scale of your y-axis is super important because you can trick people. You can straight up lie whether you mean to or not. So yeah, your graph can be used to distort the underlying data. There is a possibility that it can be done intentionally to mislead you. Now, I know everybody here trusts the media. The media would never lie, except, of course, it does, all sides of the media. There's a BuzzFeed article, and I know, BuzzFeed. Let's look at it together. A BuzzFeed article. The article is called 13 Graphs That Are Clearly Lying from 2014 by Katie Notopoulos. Looks like she just stole all her information from Reddit, just like everyone just steals information from Reddit. But that's okay. Let's look at a few of the graphs on here. Gun deaths in Florida. It's a scary idea. But look at the graph. Look at the axis on the graph. It is upside down. This way. Look at that. The 0 is at the top, and then we're going downwards to get to larger numbers. That means you need to literally flip this graph on top of its head. That means, look, it looks like the gun deaths in Florida are increasing, doesn't it? But no, it's the opposite. If you're going up, you're actually decreasing because you're going lower on the y-axis. You're becoming smaller numbers. This is a terrible graph. Whoever made this graph, it looks pretty. It's a very well put together graph aesthetically looking. The content of the graph is just awful. So, interesting idea. And there's all kinds of really bad graphs. This one, and I'm sorry, there's ads on the side. My ad blocker decided to stop working, I guess. Obamacare enrollment, if you remember that, you had to sign up for Obamacare if you didn't have health insurance. As of March 27th, 6 million people had signed up. By March 31st, 7,066,000 people had signed up. But look at that. This bar over here on the right is like 3 or 4 times higher than this bar over here. So it makes it look like this number is supposed to be 3 or 4 times. Is it? It's definitely not. Yeah. So that doesn't even tell you what the scale is on your y-axis. This is a bad graph. And Yeah, it's bad simply because it doesn't give you the proper scale. Oh, this graph. This isn't, I can't get it on to get the entire thing on here, not without shrinking the web page. But the number of people, this was a survey done, no, it's the governor race in a certain state. You have Democrat Charlie Crist, Republican Rick Scott, and unsures. 26% voted unsure, 37% voted for the Republican, and 37% voted for the Democrat. Cool. Why are these bars not the same height? Look at that. 37%. I'll tell you the real reason. It's probably because this might be like 37.1%. Yeah, and this could be 37.4% over here. So technically this bar should be higher, but because they rounded to the nearest whole percent, it just doesn't look right. So this is a foolish looking thing. Also, green makes sense for unsure. Third parties like Libertarian Party usually are called green. Blue for Democrat makes sense. Why isn't this bar red? Red for Republican. I mean, you can make it orange, but why wouldn't you just make it red? It's low-hanging fruit. So if you remember R.A. Dickey, he was a knuckleball pitcher for the Blue Jays. He won a Cy Young with the Blue Jays in, I think, 2012. Before he did that, he was just a regular pitcher, but then his arm strength decreased with age, so he tried throwing the knuckleball with great success. Anyways, look at that. His velocity on his knuckleball it dropped 2 miles per hour, but they're making it look like it fell off a cliff. So again, and that was just this was in just a Blue Jays game. I don't think anyone was trying to lie to you with this graph. I think it was just not well thought out. Should Scotland be independent? 52% say no. 58% say yes. 52 plus 58 is 110. So 110% of people are voting. That's wrong. So yeah, there's all kinds of, what should cost less, a gallon of gas or a gallon of milk? And they ask yes or no. So yeah, that's just kind of silly. What should cost more, a gallon of gas? Yes, that's what they mean. So obviously they just were not thinking. You can distort realities. So some tips for you so that you don't distort reality. Make sure the title of your graph is logical, makes sense. Don't use a title that's confusing or weird. Don't use a title that has 300 words in it. Use a short and sweet title that is accurate and not too much. Make sure the numbers line up on the vertical axis. When you're designing your graph, your visual, do not use clip art. If you don't know what clip art is, good. If you do know what clip art is, that means, like me, you used to make school reports in 1997, and Microsoft Word gave you some clip art you could use. It was just like stupid, childish drawings of things, or word art is even worse. Those are an abomination. Do not use them in your graph. Do not use them in your PowerPoint presentation. Keep your PowerPoint presentation slick. Keep it nice and smart looking, and don't use stupid graphics. Make sure the big one though is on your horizontal and also your vertical axes. Make sure you're using good scaling. Make sure your bars are proportionate, and make sure you source your information. You don't just say that, there's 10 million people in the world who are ready to hand me $50. So I'm going to have 500 million bucks here pretty soon. That's just a ridiculous claim. There's not 10 million people who are going to do that for you. So if you're going to make any kinds of claims, especially ones that are wild, you need to source them. Even if they're not wild, source your claims. And when it comes to bad graphs, you just kind of know it when you see it. You have a pie chart where each of the different slices of pie is a different color, but you just choose all shades of yellow. That's going to look like crap. Your pie chart's going to look horrible. It's going to be hard to differentiate the slices. You do a pie chart where all the slices are like neon and like neon pink and baby blue. That's going to look like crap. Keep a nice sharp looking pie chart. Do not use 3D charts. Don't use a pie chart where it looks like it's coming out of the screen at you. or that it's like been rotated onto its side, that looks corny. Don't use 3D effects. Don't try to impress a bunch of people in the 90s. This is not the 90s. We are not surprised anymore by the fact that computers can make cool graphics. We're a little bit more jaded, okay? We're a lot more cynical these days. So don't try to impress people in the 90s. Can that computer tell me who's going to win the World Series? Is it going to be the Chicago White Sox? Don't do that. Nobody's impressed anymore. All right, Goobers, that's it for today. That covers the first section of chapter 12. You guys have a lovely day.